Hi, I am Ioana and I will present our work called Cross-Model Retrieval with Query Bank Normalization. In this work, we tackle the text video retrieval problem. So, given a query and a gallery of videos, the goal is to retrieve the video that is best described by the query. Now, I will explain what is the hubness problem and how it affects the performance of text video retrieval method. In this example, we will assume we have 3 queries along with their embeddings, and 3 videos in the gallery and their embeddings. In the ideal case, each query will retrieve 1 video. So Q1 will retrieve video X1 and so on. Now we compute the cosine similarities between the embeddings. The thickness of the line denotes the magnitude of the cosine similarity. We can observe that in this case, Q1 will retrieve video X2, which is incorrect. Next, the same is done for all the queries. We observe that all the queries retrieve video X2, making video X2 a hub. This is an undesirable behavior for our retrieval method because while X2 is highly retrieved, the other videos are never retrieved. Now, let's see how the hubness problem affects current retrieval works. In this graph, we present how many times each video is retrieved. We observe that there are several videos that are highly retrieved, while if we look at the right side of the graph, almost half of the videos are never retrieved. The same phenomenon happens for all the studied methods and also on all other datasets. You can find the entire study in the paper. Now, let's see how we can use query bank normalization, shortened QB-norm, in order to mitigate the hubness problem. QB-norm can be applied to any retrieval method and does not require retraining. First of all, a query bank needs to be defined. It can consist of training queries or, in the real-world scenarios, past queries. Next, we compute the similarities between each query from the query bank and each video from the gallery. Computing the similarities between queries from the query bank and the video gallery can be done in the pre-computation step. Next, let's see what happens at inference. After computing the cosine similarities, we normalize them using QB-norm. As you can see, applying QB-norm, the similarities are normalized and now Q1 correctly retrieves video X1. The same happens for all the queries. And you can observe that the normalized similarity retrieved the correct videos. Also, please observe that video X2 is no longer a hub. In conclusion, by applying QB-norm, we reduce the influence of the hubs by normalizing the similarities. QB-norm is a framework that works with any retrieval method and with different normalization techniques. Next, I will present our proposed normalization technique, which is more robust, called dynamic inverted softmax. Here is another example. In this case, Q2 and Q3 retrieve the correct video, while Q1 incorrectly retrieves video X2, making X2 a hub. As presented before, we compute the similarities between the queries from the query bank and all the videos from the gallery. We first observe which videos are retrieved using queries from the query bank and thus prone to be hubs. The videos that are retrieved will form the activation gallery. This can be done in the pre-computation step. Now, let's see what happens at inference. We look which queries originally retrieved videos from the activation set. In this case, only Q1 and Q2 retrieve videos from the activation set, so we want to normalize only those similarities. In conclusion, using dynamic inverted softmax, we normalize only the similarities that retrieve videos from the activation set. Dynamic inverted softmax has an increased robustness to potential harmful query banks. Now, let's see how the query bank can be constructed. We can observe that by using the training queries, we obtain a boost in performance. Other works for the task of text video retrieval assume access to the test queries, which may be unfeasible. However, we proved that an efficient query bank can be constructed from the training queries. As it comes to the results, we show in extensive experiments that using QB-norm the performance increases and also the hubness problem is mitigated. In our paper, you can find results using more methods and on more datasets. Furthermore, we proved that QB-norm can be successfully applied on other retrieval tasks. In conclusion, we showed that recent retrieval works suffer from the hubness problem, and QB-norm can be successfully used in order to mitigate this issue and increase the performance. Thank you for listening. Our code and data can be found online.